So in the previous video we have seen randomized quicksort, where we picked a random pivot and partitioned and sorted recursively on the both sides. So we said that so it will be good to choose this pivot carefully, so that when you do the partition, it actually divides the array into almost two equal halves. We said we will in this video and in the next few videos we will learn how to achieve this. In particular, we will look at an algorithm which finds the median in linear time deterministically. So once you have a linear time algorithm to find the median of the given sequence of numbers, then we can replace the random pivot function with the median function and then partition, so that way by the definition of the median, so it will divide the array exactly into two halves. So before we talk about that particular algorithm, we will define the notion of rank, which in some sense generalizes the notion of median. The rank of a number is defined as 1 plus the number of numbers which are greater than that particular number. So the rank of a maximum number will be 1, and rank of a minimum number in a given collection of n numbers will be n. So if you take the median, that is an element with the rank n by 2, so that will be the median. We will define the term rank more formally here, and we will see a randomized algorithm which can give us a number which is greater than the median very efficiently. So given a collection of integers, let's say that you are given n sequence of integers a0, a1, a of n minus 1, given an x, this x may or may not be there in the collection, then the rank of x is defined as the number of elements which are strictly greater than x plus 1. I repeat, the rank of a number is defined as 1 plus the number of elements in the given set of elements which are greater than x. For example, if the given set is 12, 38, 28, 33, 22 and 23, and if we are given 32 as our number, then if you are asked to find the rank of x, then what you can see is that the numbers which are greater than 32 are 38 and 33. So there are exactly two numbers, that is 32 and 33, which are greater than 32. So the rank of 32 is 3. So as an example, if you consider the set of students writing an exam, the rank 1 guy is the person who has got maximum number of marks. So if the person who has secured the maximum number of marks, the number of people who have scored more than him is 0, so the rank of that person is 1. Similarly, rank 2 person is a person such that there is exactly one person who has scored more than him. Similarly, rank 10% is a person such that there are exactly 9 people who have scored more than him. So in general, rank of a number is defined as 1 plus the number of numbers which are greater than x. So you can notice that if I give you the maximum number, the rank of that is 1, and the minimum will have a rank n, exactly n, because if you look at the minimum number, all the n minus 1 numbers except this are greater than this number. So if you take any number which is a minimum, or any number which is smaller than the minimum, the rank of that number will be n. So similarly, the median will be an element whose rank is n by 2. So if I had to given a collection, if I give you an x, it's easy to find the rank of x using a linear time algorithm. You can start with r is equal to 1, then for I is equal to 0 to n, you just check whether how many numbers are greater than x. If a of a is greater than x, then you can increment the counter r plus plus. So at the end of this algorithm, the rank, so whatever is the rank, that will be the rank of the given x. So now let's look at the other problem. So we are given an integer r which is between 1 and n. We would like to find an I such that the rank of a of I is r. In other words, we would like to write a function which is called as a find rank function. We will take an integer, the range for the integers is between 1 and n, and it should return an index I, okay, such that if I go and access a of I, this will be an element whose rank is R. So let's look at an easy algorithm. So if I look at the easy algorithm, let's sort the sequence in the increasing order. If I sort the sequence in the increasing order and if I want an element whose rank is R, the claim is that you have to return n minus R. Okay, so let's look at n minus rth element, this element. So all the numbers to the right of it are all greater than this a of n minus r. So the number on the right hand side, this index is n minus r plus 1. The last index is n minus 1. So the number of numbers which are all greater than a of n minus r is n minus 1 minus this number plus 1, right? So this will tell us the number of numbers which are greater than a of n minus r, right? So in general, if I give you an index a and an index b, then the number of numbers between a and b, including both endpoints, is b minus a plus 1. Here b is n minus 1, a is n minus r plus 1. So the number of numbers which are strictly greater than a of n minus r is exactly equal to n minus 1 minus n minus r plus 1 plus 1. And the rank is defined as the number of elements which are greater than this number plus 1. So I add the plus 1. So all the 1s and n's can cancel. What you get is r. So if you want to find the an element whose rank is r, once you sort, you just have to report n minus r. So there is an another algorithm to compute the find rank. So the algorithm is simple. You sort a sequence and then just report n minus r. But this algorithm takes n log n. But is it really required to sort the given sequence if you have to find the find rank? So the note is that once you sort the sequence, for every r you will be able to find the find rank of r in order 1, right? So this sorting, in some sense we are doing much more than what is required. Okay, so the earlier definition works perfectly fine if a of i's are all distinct, but if a of i's are repeating, then we can define the rank of r as the element which is at n minus rth location in the sorted sequence. I repeat, so if you look at the even if the sequence is repeated, if there are repeated elements in the given sequence, so once you sort it, the rth element here will have the rank n minus r. So that's the way we can define the sorted sequence. So in the next video we are going to see how to find the rank given r in a linear time. So now let's pay an attention to one interesting problem. Given a sequence of numbers, I want a number whose rank is smaller than n by 2 plus 1. So n by 2 plus 1 is the rank of a median. So what I am looking for is a number which is bigger than the median, right? So the example could be that there are about 50 million people paying income tax in India. So we don't know how much each of these individuals are paying. We don't even know the median. But so given the amount of tax 50 million people have paid, so we want to just get an idea. So you just want a number which is bigger than the median. So what's the problem? You're given a sequence of numbers, and the problem is we need an algorithm which gives us a number which is certainly bigger than the median. Let's think of an easy algorithm for this. So let me pick a random p between 0 and n minus 1. So what is the probability that a of p is smaller than the median? So since you know that the median is the number, there will be exactly half the numbers which are smaller than the median, exactly half the numbers will be bigger than the median. So if I pick a random element from the given set of numbers, then the probability that this is smaller than the median is exactly half. The probability that it's greater than the median is also half. So with if I had to give you a number which is bigger than the median, if I randomly pick one of the numbers and give it to you, the probability that this is the right answer is 1 by 2. So we repeat this experiment k number of times. Let me pick k numbers from the given randomly from the given sequence of numbers. So what is the probability that all of them are smaller than the median? The probability that one of them is smaller than the median is 1 by 2. So the probability that if I pick two of them, both of them are smaller than the median is 1 by 2 into 1 by 2. I am assuming that the k numbers are chosen independently at random, right? So if I choose k numbers, the probability that all of them are smaller than the median is 1 by 2 to the power k. So saying the same thing differently, then so if I pick k numbers from the given sequence of numbers, then the probability with probability 1 minus 1 by 2 to the power k, at least one number will be greater than the median. I repeat, if I pick k numbers uniformly at random, if I pick one number uniformly at random, the probability that it is smaller than the median is 1 by 2. If I pick k numbers, the probability that all of them are smaller than the median is 1 by 2 to the power k, which also means that if I pick k number, then the probability that at least one of them will be greater than the median is exactly equal to 1 minus 1 by 2 to the power k. So the algorithm is simple. So what I do is that I pick k numbers uniformly at random and report the maximum of them. Since at least one of them, if at least one of them is greater than the median, then obviously if I choose the maximum, that will be bigger than the median. So from the previous slide, what it means is that if I pick k numbers and keep track of only the maximum number and report the maximum number that I have chosen, then with probability 1 minus 1 by 2 to the power k, then whatever the algorithm reports will be a number which is greater than the median. I repeat, so you are going to choose k numbers uniformly at random. So as and when you choose these numbers, you only keep track of the maximum number and report the maximum number. So what we are saying is that this algorithm will give you a number which is greater than the median with probability 1 minus 1 by 2 to the power k. Now let's just plug in the value of k is equal to log of n. So if I just plug in the value of k is equal to log of n, then I will be picking log n numbers uniformly at random, and the probability that the maximum will be greater than the median is 1 minus 1 by n. So if n is as large as a million, then so with probability 1 minus 1 by 10 to the power 6, the number that I am reporting will be a number which is greater than the median. In the income tax example that I give you, if n is 50 into 10 to the power 6, then if I just choose about 26 of the numbers, then what you can see is that with probability 1 minus 1 by 50 into 10 to the power 6 probability, the number that we are going to choose will be a number which is greater than the median. So in summary, what we have is a randomized algorithm here, which picks only the log n number of numbers uniformly at random and keeps up the maximum and reports the maximum number. So this will be a number with which is greater than the median with very high probability, the high probability being 1 minus 1 by n. In other words, we have a randomized algorithm which only takes order log n number of comparisons and gives you a number which is bigger than the median with a very high probability. But if you want a deterministic algorithm which for sure gives you a number which is greater than the median, the claim is that such an algorithm takes omega of n number of comparisons. So let's look at a deterministic algorithm which gives you a number which is bigger than the median. The claim is that it has to do at least n by 4 number of comparisons. If you take any algorithm which does n by 4 number of comparisons, each comparison it requires two numbers. So it will only look at most n by 2 elements. So since the algorithm is deterministic, given a sequence of n numbers, so well in advance I can know that these are the n by 2 locations, the elements at these locations will be compared. I repeat, the algorithm does only n by 4 number of comparisons, so it has to look at most n by 2 elements. So since it's a deterministic algorithm, before I give you the sequence, I know that these are the less than n by 2 locations. The algorithm will look at these elements and give us an element which is greater than the median. So what I do is that I look at all these locations with the number of locations that are going to be there is smaller than n by 2. So I'm going to place the numbers which are all smaller than the median in these locations. Since there are n by 2 numbers which are smaller than the median, I can place these numbers in the locations where the algorithm is going to make the comparison. So by looking at these less than n by 2 locations and doing less than n by 4 comparisons, so whatever the algorithm gives for sure will be a number which is smaller than the median. So the conclusion is that if I have to get a number which is greater than the median, any deterministic algorithm should necessarily do at least n by 4 number of comparisons. In other words, the lower bound for this problem is omega of n. Any deterministic algorithm which gives us a number which is greater than the median has to do omega n number of comparisons. But what we have seen is that we have shown a randomized algorithm which in order log n time gives a number which is greater than the median, but there is a small probability, very small probability that the answer that is given to us is wrong. So in practice, it's better to live with a order log n algorithm which does mistakes very rarely, rather than living with an algorithm which is a deterministic algorithm. In summary, so there are two kinds of randomized algorithm. Randomized algorithm is a algorithm which makes some random choices during the execution of the algorithm. There are two kinds of randomized algorithms. One is called as the Las Vegas kind of algorithm. Another one is called the Monte Carlo algorithm. In the Las Vegas kind of algorithm, the algorithm always gives the correct answer. But the running time of the algorithm will depend on the input and the random choices the algorithm does. For example, we have seen the randomized quicksort. The randomized quicksort is expected to sort this given sequence of algorithm all the time. But only what is not guaranteed is the running time of the algorithm. In worst case, this can take order n square time, but in the last video we have seen that on average it takes only n log n. So on average the running time is an expected thing, but it always gives the correct answer. In the next video we will also look at a linear time algorithm for the find rank, which is also on average it's going to be linear time, but in worst case this can be order n square. We have also seen another kind of data structure called hashing, which on average does very well. So algorithm always gives the correct answer, but the running time in worst case can be very bad, but on average these are very good compared to the corresponding deterministic algorithms that we have. So the Monte Carlo algorithm on the other hand are very efficient in general, but the answers are wrong with a very low probability, right? So when the algorithm gives an answer with the answer is correct with a very high probability. So the algorithm that we have discussed in this video, which gives an elements which are better than the median. If you want a deterministic algorithm, so what we have shown is that any deterministic algorithm will do at least omega of n number of comparisons. But we have seen a order log n kind of algorithm which will give the correct answer with a high probability being 1 minus 1 by n. So there is also a famous problem called primality testing. In the primality testing, we are supposed to given a number, we want to decide whether it's a prime or not. So there is if you need a deterministic algorithm, then the best algorithm has a complexity of k to the power something like 6, where k is the number of digits in the given number. But if you are willing to settle down for a randomized algorithm which mostly gives the correct answer with a very high probability, then there are algorithms which are faster than k cube, right? So if you want a deterministic algorithm, you need to spend k to the power 6 time, but if you are willing to live with a randomized algorithm, Monte Carlo algorithm, when the algorithm says that it's a prime, it is a prime with a probability 1 minus 1 by n, then you can design algorithms which are much more efficient compared to the corresponding deterministic algorithms. So in this video we have seen so what is the rank and We looked at algorithm to compute an element whose rank is smaller than n by 2. So which basically means that we were looking for an algorithm, efficient algorithm to find a number which is greater than the median. So if you are willing to settle down for a randomized algorithm which makes a mistake with a very high, very low probability, in other words the algorithm gives the correct answer with a high probability, then we can design a algorithm which is as efficient as order log n. More particularly, we have seen an algorithm, order log n algorithm, which gives the which finds an element which is greater than the median with probability 1 minus 1 by n. And we have also seen that this kind of algorithms are called as Monte Carlo randomized algorithm. These are efficient algorithms which will give correct answer with a high probability. So we have also summarized, so there are two kinds of randomized algorithms. One is the Las Vegas kind of randomized algorithms where the algorithm always gives the correct answer, but the running time of the algorithm will depend on the input as well as the random choices the algorithm does. But whereas in the Monte Carlo algorithm, you have a control over the running time of the algorithm, but you are not guaranteed to get the correct answer all the time. But there is a guarantee that you will get the correct answer with a very high probability.